Voice over IP is the technology used to carry phone calls over the Internet. Thanks to its bandwidth efficiency and low cost, VoIP is increasingly common as an end-user technology where subscribers directly use their VoIP phones in the same manner as a traditional PSTN, or where businesses replace their PBXs with VoIP-enabled PBXs. It is also used as a backhaul interconnect technology within a carrier voice network or interconnecting carriers. This session will provide an overview of VoIP technology fundamentals. First, we will look at some IP telephony basics. Then we will look at speech encoding and codecs. Next, we will see how speech is packetized and then transported. There will then be an overview of Session Initiation Protocol, which is one of the most widely deployed VoIP signaling technologies available. VoIP technology routes phone calls over existing data or IP networks. The voice is first digitized and compressed, then encapsulated into IP packets. These packets are then transmitted over the IP network, possibly through different paths, to the final destination. Because of the lack of quality of service or QoS control between the source and destination, the IP packets transmitting voice are subject to the same network impairments as data packets, but the nature of a voice conversation makes it immediately noticeable to the end user. Some of the impairments associated with VoIP include the following. Packets can be lost during transmission, which can create noticeable gaps in the speech. Because of the varying time and path of the packetized voice packets, jitter can be present at the receiver. Because the voice packets need to be played out at regular intervals, this requires a de-jitter buffer at the endpoint. The de-jitter buffer may introduce additional delay or dropped packets if the packet jitter is excessive. In addition, excessive end-to-end transmission delay can be present, especially in congested networks. Excessive delay will impair interactive conversation between the caller and the callee, where they will be interrupting each other and where any echoes will be more noticeable. We will now look at speech encoding and codecs. Speech encoding is used in IP and mobile telephony to compress and encode human speech before it is transmitted through the network. The G711 codec is commonly used to digitize a voice conversation for transmission over IP. With the G711 pulse code modulation, or PCM codec, 8,000 samples per second are taken from the analog voice signal, equivalent to a rate of 8 kHz. A sample is a measurement of the level of the analog signal. This sample is then converted into an 8-bit sample. These samples provide 256 different levels of the analog signal. The G711 mu-law algorithm is used in North America to map the voice spectrum into these 256 different levels. Once converted into a digital signal, the voice stream is packetized into IP packets to be transmitted on the network. Different encoding techniques achieve different results, usually with a trade-off between speech quality and bandwidth utilization, computational delay, and complexity. G711 PCM encoding produces good quality speech but relatively poor bandwidth usage at 64 kilobits per second. It is generally seen as a toll quality codec and has a median opinion score, or MOS, of 4.2 when no external impairments are present. MOS is a commonly used voice quality metric that rates voice quality on a scale from 1 to 5, with 1 being the lowest. Many other codecs can be used for VoIP. Here are a few examples. Codecs such as G723.1 or G729 achieve better bandwidth performance, but have worse speech quality than G711 PCM. Their MOS scores are 3.8 and 3.9 respectively, when no external impairments are present. The G711 PCM codec is a commonly used waveform codec, with two different versions available. The G711 mu law is used in North America, and the G711A law is used in the rest of the world. There is a slight difference between the two codecs in the way speech is encoded. G711 has a sampling frequency of 8 kHz and a bandwidth of 64 kilobits per second. Each RTP packet contains 20 milliseconds of speech, which is its packetization time, or P time. The typical algorithmic delay for G711 is 0.125 milliseconds. Algorithmic delay is the time it takes to encode the speech with the codec. Another speech codec is G723.1, which is mostly used in voice over IP applications because of its low bandwidth requirements. There are two bit rates at which G723.1 can operate: 6.3 kilobits per second using 24 byte frames, and 5.3 kilobits per second using 20 byte frames. Like G711, G723.1 has a sampling frequency of 8 kHz. G723.1 Annex A supports silent suppression, which reduces bandwidth by stopping packet transmission during silence periods. The algorithmic delay is 37.5 milliseconds per frame, and G723.1 has a P time of 30 milliseconds or multiples of 30 milliseconds. Music or tones, such as DTMF or fax tones, cannot be reliably transported with G723.1 because of its low quality encoding. Another speech codec is G729. Because of its low bandwidth requirements, G729 is mostly used in VoIP applications where bandwidth must be conserved. G729A, an extension of G729, has a sampling frequency of 8 kHz. It requires 10 millisecond frames. G729A has a fixed bitrate of 8 kilobits per second for the 10 millisecond frames. The algorithmic delay is up to 20 milliseconds per frame. G729A is a compatible extension of G729 that requires less computational power. The trade-off for this lower complexity, however, is that it has reduced speech quality. Another extension of G729 is G729B, which provides a silence compression method. G729AB combines the features of both G729A and G729B. Tones such as DTMF and fax transmissions, as well as high-quality audio, cannot be reliably transported with a G729 codec because it encodes at a low quality. We will now look at how speech is packetized and transported. As this graph shows, the continuous digitized speech is broken down into frames containing a certain speech duration, usually 20 milliseconds or 30 to 40 milliseconds. The amount of speech contained in a frame is described as the packetization time, or P time. The speech frames are then encapsulated to be transmitted on the network through Real-Time Transport Protocol, or RTP, and User Datagram Protocol, or UDP. The picture here shows the details from a packet capture protocol decode. In addition to the IP header used to route the VoIP on the IP network, the frames are encapsulated with a UDP header and an RTP header. We will see the details in following sections. UDP is a Layer 2 or Transport Layer Protocol documented in the IETF standard RFP 768. UDP provides no guarantees for message delivery, and a UDP protocol layer retains no state of UDP messages once they are sent. It provides application multiplexing by keeping track of the port numbers and error verification through a checksum of the header and the payload. Because of its properties, UDP is used for real-time applications that can tolerate a small amount of packet loss, such as VoIP or IPTV. UDP has 4 header fields. The first is the source port number, which identifies the sender's port number. The second is the destination port number, which identifies the receiver's port number. The length field identifies the length of the UDP datagram, which consists of the header and the payload. Finally, the checksum field is the checksum for the UDP datagram. Real-time Transport Protocol, which is specially designed for the delivery of real-time applications, is defined by IETF standard RFP 3550. RTP provides end-to-end delivery services of real-time audio encoded through G711, G723.1, G729, and many other codecs, as well as video encoded through H.261 or H.263. This RTP data is transported using UDP. RTP includes 3 header fields. The payload type field indicates the codec used in the payload. The timestamp field is used by the receiver to synchronize so that it can play back at the appropriate interval. The sequence number field, which allows the receiver to detect packet loss or out-of-order packets, changes by increments of 1 for each RTP packet. The timestamp and sequence number fields are used to compensate for possible network impairments, such as packet loss, out-of-sequence packets, and jitter. The Real-Time Transport Control Protocol, or RTCP, is also defined in IETF standard RFP 3550. RTCP provides out-of-band statistics and control information for an RTP flow. Using RTCP is not mandatory. Its primary function is to provide feedback on the quality of the data distribution. The picture here shows the details from a packet capture protocol decode of an RTCP packet. Session Description Protocol, or SDP, is defined in IETF standard RFP 4566. SDP is used with RTP at the beginning of a session. SDP does not itself deliver media, but is instead used for negotiation between endpoints of media types, formats, and all associated properties. The picture here shows the details from a packet capture protocol decode of an SDP packet. SDP is used between the call's endpoints to negotiate their capabilities prior to establishing the phone conversation. For example, SDP can negotiate which codec will be used and whether or not fax will be supported. The two endpoints must agree on a common set of capabilities before the call can be finalized. The SDP is often embedded in the call invite message sent by the caller. In this section, we will describe how the call is established end-to-end between the caller and the callee. Several signaling VoIP technologies are available, with the Session Initiation Protocol, or SIP, and H.323 as the most commonly used. Here, we will describe SIP. The Session Initiation Protocol is defined in IETF RFC 3261. SIP is an application layer protocol used for the setup and signaling of VoIP calls. It is used in conjunction with UDP for transport, RTP and RTCP for media transport, and SDP for session negotiation. SIP is close to HTTP and SMTP-based protocols with an HTTP-like format where the client makes requests and gets responses from the server. SIP messages are exchanged between the SIP endpoints, which are the phones, and the SIP elements, which are the SIP servers, to establish the call. When the call has been established, media, which is RTP packets with a voice payload, is exchanged between the endpoints. Here is a list of the most common SIP network elements. First, the SIP endpoints, also commonly called the user agent or UA, can be a SIP phone or a soft phones application running on a PC. The registrar is a server that receives the register request sent by the UAs and keeps track of where to locate users. The SIP proxy receives and forwards requests, as well as sending queries to the registrar to locate users. The redirect server responds to location requests if a user has multiple addresses, such as work or home. Often, the proxy, registrar, and redirect servers are located in a single server. The session border controller can be used in the network to provide services to the connected user agents, such as security topology hiding or NAT traversal. Finally, gateways provide the interconnect function between SIP and other network types, such as a PSTN or H323. The simplicity of the call setup with SIP has been a factor in its success. Only 3 messages are necessary to set up a call between 2 endpoints. SIP uses UDP, or Transmission Control Protocol, as a transport protocol. In this example, the first message, which is from Terminal A, is the invite initiating the call. The second message is the OK, the response from Terminal B to Terminal A. The third message is the confirmation from Terminal A. The session description protocol embedded in the SIP message determines the codec that is used. All SIP messages contain to and from fields, which are the Universal Resource Identifier, or URI. A SIP URI is equivalent to a SIP phone number, and its format contains the fields user@domain. The user fields can be a username, a phone number, or an IP address. The domain is the host providing the SIP resource, containing either a fully qualified domain name or a numeric IPv4 or IPv6 address. The address can also contain a port number where the request needs to be sent. The chart here shows a typical SIP call flow between 2 endpoints. First, the registrar receives the register request and sends a response. Then the caller sends an invite with SDP embedded in the SIP message to the proxy, which then goes to the callee after it has been found. The second message is the OK response from the called party. After it receives this message, the calling party returns a confirmation message. The call has been established, and speech media within the RTP payloads are exchanged between the 2 callers. Note that this call flow involves a registrar and a proxy, although their functions are often combined into a single server. At the end of the call, whoever hangs up first will send a bye message to the other party, who in turn acknowledges it. In this session about Voice over IP technology, we looked at some IP telephony basics. Then we described how speech is encoded and some codecs that can be used for VoIP, such as G711PCM, G723.1, and G729. We then looked at how speech is packetized and then transported with RTP and UDP. There was then an overview of Session Initiation Protocol, a widely deployed VoIP signaling technology, and saw a simple example of a SIP call flow. For more information, contact VX at 510-651-0500 or on our website at www.vxinc.com.